write down extra things that I'm saying that go with the notes, right? So just kind of keep some of this stuff in mind as we move forward. All right, so we know, oh, I should probably share the screen. Okay, we know the traditional definition of the derivative, right? We've been working with that, and that is here. And this was one way to write, to indicate it. F prime of x is the way we said it. F prime of x, that is the derivative, right? As you can see on your screen, other notations that all mean the same thing. Okay, F prime, y prime, dy dx. We're going to get into that here in a little bit. In this case, df dx. Or we could say d dx of f of x. These are less common, to be really honest. And the fact is, the ones that I highlighted for you in green are the most common ones that you will see and need to become familiar with, okay? So the prime, this f prime or y prime, that indicates the derivative. This is a new one you really haven't seen yet, dy dx. And then d dx, we're going to be using quite a bit as we move forward, all right? And on the rest, did I give you the bottom of that screen? I did not. Okay, so let's add this to it. Okay. So when you see something like this, and you have a vertical bar next to it, it's saying, the vertical bar is saying, evaluate the derivative at x equals a. A lot of the times it'll be a specific number, and eventually I'll show you how to do this in your calculator when we get to that, which is nice because it can be done on the calculator. But oftentimes, like even on the quiz you just took, you had to evaluate the derivative at a given value, right? And that's what this is another way of saying. Evaluate the derivative at whatever the a value is, right? So this notation is new. Like I said, a lot of this notation is new. Now, I alluded to this the other day when we look at a graph. There are certain things that we need to look for to decide whether or not a specific value is differentiable, okay? Or it is differentiable at that value, okay? And so there are certain times when a function does not have a specific derivative at that value. And the first one that I gave you was if it's not continuous. Okay, so this is an example that this derivative will not be continuous at a, right, because there's a discontinuity. It would be, you could find the derivative at any of these other values or any of these values because it is continuous, but at a, it's not continuous, therefore it is not differentiable at a. The next one I gave you is when we have a sharp turn or a corner, and when we looked at that velocity graph the other day, when we were talking about putting parentheses versus brackets because we had sharp turns. And so at this particular point right here, at a, it's not going to be differentiable. The book calls it a corner. I like to describe it as a sharp turn. Previous generation used to call it a cusp, but that's just not really a commonly used word anymore. All right, but if you see or hear any of those, that's what you want to call it. Okay, that's where we know that it's not differentiable. And then the last one is it has a vertical tangent at a. Okay, and so let's understand what that means. What is the slope of a vertical line? There's no slope. It has no slope, okay? A vertical tangent has no slope. What does have slope? 0? Horizontal line, okay? And we're going to talk about, we've talked about horizontal tangents already. So if there's a spot on the graph where there is a vertical tangent line, then that spot is going to indicate it is not differentiable there, right? Those are the three kind of look fors, all right? Now, one of the things that we started doing in 2.7 was taking a graph and then creating its first derivative graph. That's what we were doing when we took position and then we graphed velocity. We were graphing the derivative. Okay? And so what we're going to be doing here, and I think I gave you all of these. Let's see how far we got to go. We'd like to hear one more. This is what you have, right, as your next slide? Okay, so this is the graph of f of x. Over here, we are going to create the graph of the derivative of f. And these are the things you want to look for. You want to look for a horizontal tangent, because what is the slope of a horizontal tangent? 0. The slope of a vertical tangent. What happens when you have a vertical tangent on the derivative? No. It's not, you can't find the derivative. There is no derivative when there's a vertical tangent. And so that's going to indicate a place where there might be a hole in the derivative graph or some type of discontinuity. It doesn't have to be a hole. All right. And then the slopes of 1 and -1, I like to look for those because to me those are the easiest ones. We know that the slope, when a line has a slope 1, it's like a 45-degree angle, right? And then when the slope is -1, we just flip that line and it's going the opposite direction. So we're going to work through this problem together. The first thing I want to do is look for horizontal tangents. And what we used to call this in algebra is when the parabola touched the x-axis, right? So when I look for horizontal tangents, I'm looking for spots where I can draw in horizontal lines. And so what we're going to end up doing is on this graph to the right, we're going to make a graph of the slopes. That's essentially all we're doing. The slopes of the tangent lines. I guess I should have added that too. Should be slopes of the tangent lines. That's what this graph is going to be. A graph of the slope of the tangent lines. And so the reason why I like to use the horizontal tangents first is because the slope of those is 0. And so wherever I have horizontal tangents on that graph, I'm going to have corresponding points where y is 0. Okay, so here's where those are going to be. The one thing you have to understand about when you look at the graph for the derivative versus the function, or vice versa, is it's never going to be perfectly exact. You're looking for trends. And so here, to me, are 3 horizontal tangents. Right? And so what I can then do is associate zeros with those. Okay? So in other words, right here, about halfway, I'm going to have a point 1/2, 0. I'm going to have another point here about 1.5, 0. I'm going to have another point 3, 0. Okay, so those are going to line up because the slopes at those horizontal tangents are 0. Okay, does that make sense? Now, I don't see any vertical tangents necessarily. If this thing went further, then we might have one over here. If this thing went further up, we might have one over here. But for now, I don't see that. Okay. So the next thing I'm going to do is look for places where the slope is 1, where I can make basically a 45-degree line and make it touch the graph somewhere. Okay. And so I see a couple of those. I see one there and there. Again, it's approximate. You're just trying to kind of eyeball it, and those are about 45s. And so what I say is, so what is the slope of this line? It's 1. So I have to then find the corresponding x where I can put a 1. This looks like it's about 1, 1. So at x is 1, the slope is 1. This one's like 2, 3, 4, and a little more. And that's where the slope is going to be 1. So I have 2 points then that correspond to those. Notice that the y value for both of these is 1. Slope is 1, slope is 1. The x values coincide. Okay, question so far? Yes?
For the second red dot, why is it farther? Like, how did you get the x value for that?
Right here, this x value right here.
Okay. Alright.
So whatever this x value is, that's why it lines up here. This x value here is about 1, so it's there.
Okay.
And again, keep in mind, when you do these graphs, we're looking for a similar shape. It doesn't have to be perfect, all right? We expect some deviations along the way. All right, now -1. How many do you think there are? Slope is -1, tangent lines. What do you say? I heard 1, I heard 2, I heard 3. I say there's 2. I'm not sure where you get a third one from. These are really steep in here. This is much steeper. Okay, so again, x is 0. What is the slope for this line? -1. And this one's like 2.5, -1. So that means I'm going to have points down here. And this is enough. We have enough information now to kind of connect the dots. So the slope of all of these tangent lines we can use to approximate over here this graph, and then we just connect them. Where did it go? Oh, we had a couple more. I put a couple more on here. Look at that. What kind of slope does this have? Positive or negative? Is it going to be smaller than -1? So, right, we're guessing here, right? We could say -2, we could say -3. How about this one? Steeper than 1, right? So maybe 2, maybe 3, okay? So this is where it gets a little trickier, all right? So I put this one as a little bit more than 2, and this one a little bit less. Right. So now I've got everything. I've got some good shape because this is the steepest one, these two, and so I can kind of bottom it out and sort of take the maximum slope, if you will, for this graph. And then I just can connect them. All right. It's not going to be perfect looking. But essentially what this would say is if I wanted to find slopes along the way, I could identify the slopes, which those are the derivatives at 5 or 4 or 3 or 1.5. Those are the derivatives for this graph. Okay, that's all that this is. This is technically it's the first derivative of f of x, and we'll get to that here in a second too. Okay? So the next one is for you to try. What do you notice about this graph right away in terms of derivatives? Is it going to be differentiable everywhere? Where won't it be differentiable? At that corner. Where's that corner for x? 0, okay? So what that tells us is that on this first derivative graph, there is not going to be a point on the y-axis because it is not differentiable here. Bless you. Okay, so that's important. All right, what I want you to do is kind of try your best to draw some tangent lines in there, find the slopes of those, and then match it up to your first derivative graph real quick. Take a couple minutes to do that. Yeah, that would be my hint. Just deal with one side first, find the slopes of those lines and graph them, and then see if you can have a good sense of what happens with respect to reflections to the other half. That'll be the hint I'll give you. Your best approach is to draw tangent lines on the graph, and that'll give you an idea where your points should be on the derivative graph. Draw some tangent lines. So let me walk you through what I did. Now I put, as you can tell, I marked off some values on the y-axis. And so, again, you want to look for some of those things. There's no vertical tangent here, except actually, you could think of a vertical tangent right here, but we've already talked about it not being differentiable, even though it's a corner. There are no horizontal tangents. And then the rest of it is, what is happening? I'm going to focus on this side. What is happening to the slopes as we move along this graph? Are they getting bigger or getting smaller? They're getting smaller. So when we start off at a vertical tangent, that number is going to be very close to a very big number. And then as it works its way to the right, the slope kind of goes down. So I drew several vertical tangents in. I drew, looks like 5. One here, which this one here is very steep. Then it starts to get more shallow and shallower and shallower. So what that means, let's understand what that means. As x gets bigger, the slope gets smaller. But in all cases, it's positive. So as I move my way this way, this value starts at its highest, very close to the y-axis, and it just shrinks from there. So it kind of looks something like this. Now, I did a lot of different points. Way more than I needed to. But notice here what I did put. I put an open circle because it's not going to actually ever touch the y-axis. Now, you can draw that as the y-axis being an asymptote, a vertical asymptote too, without putting the open circle, but I wanted just to be clear that it never does touch the y-axis. And so again, as x gets bigger, y is getting smaller. And so I approximated the slopes of these, and that's what I got for that part of it. Now, what's the relationship? What kind of slopes do I have here? Negative. So as x is getting bigger, see, as I move this way, x is getting bigger. What's happening to the slope? Are they getting more negative or less negative? Okay, so here, it's a low sort of negative number. But as I get here, this could be more like -4 or -5 or -6. Up here, it's kind of flatter, so it might be more like, -3/4. So it's getting more negative as x gets bigger. Another way to look at it, as x gets bigger or x gets smaller, the slope is getting bigger. So the slope here is as small as it probably will be, and as I move this way, the slope gets bigger because it's getting closer to 0. So there's a reflection, and it flips the other way. Okay. And essentially that's what my graph would look like. I would connect those dots. I did not connect them, just for the sake of it. If you did, that's fine. Right? That's kind of what the slope graph would look like. The relationship between the function and the derivative. Now, on the next slide, you are given, and this is a very common thing that they ask on the exam. They give you functions, and they give you its derivative function. And what you have to decide, okay, these are the original functions, which one matches up? Which graph, which slope graph does this match up to? Now, here's the way that I would do this, okay? The easiest way to do this. First off, do you notice anything about these 4 graphs here in particular that seems unusual compared to the rest of them? One of these is linear? No, none of these are linear. Yeah, the corners. I've got corners here. What does that tell me? There's going to be spots where it's not differentiable. Okay, so I look over here and go, all right, are there any spots where it's not differentiable on these 4? Because these are the graphs of the slope. Yeah, right here I got spots where we're not differentiable. We don't have a slope. That's why it's an open circle. So that part's easy to figure that one out. Okay, look for horizontal tangents, because horizontal tangents tell me when it's going to touch or cross the x-axis, because the slope is 0. So like this one has how many horizontal tangents? How many zeros do I have on this graph? 1. How many graphs do I have, or how many zeros do I have over here? How many zeros do I have over here? Okay, 3. So I'm looking for a graph that only has 1 horizontal tangent. I'm looking for a graph that has 2 horizontal tangents. I'm looking for a graph that has 3 horizontal tangents. Finish the problem. Since we already did B, we said that was 4. 4 was B. Okay, so look, I went ahead and actually drew them in. I drew the horizontal tangents in. I drew the spots where it wouldn't be differentiable. Okay, so since this has 2 horizontal tangents and this one has 2 zeros, they have to line up. This has 1 horizontal tangent, 1 0, 3, 3. Now, one thing that I'll warn you about is sometimes you will have to look further than that. In this problem, we don't have to look further than that because our choices are limited. But oftentimes you'll have to look more than just at horizontal tangents and vertical tangents. You might have to, estimate some of the slopes like we did earlier on that other problem, and then try to figure out where about it's 1. Okay, and so here's what you should have had. Okay, how many had that? Okay, good. All right, next we're going to talk about something sort of new. I've been intimating it as we've been talking. Velocity is the first derivative of position. Okay, we've talked about that already. When you take the derivative of position, you get velocity. Now, the word that we've introduced here is the first derivative, which implies that there is a second derivative, which there is. Okay, and there's third derivative and fourth derivative and fifth derivative, etc. All right. So first off, acceleration is the derivative of velocity. So when I have velocity and I take the derivative of that is acceleration, which means the acceleration is the second derivative of position. So for those of you who are taking physics, all right, you probably know this relationship already, but you didn't know it in terms of a calculus definition, right? If you take the second derivative of the position of something as it's moving, you will find its acceleration at that given instant. Okay? So that's the relationship there. And then the last thing that I put up here, and again, I gave this to you, but this is notation. Okay, so let's be clear about this. 2 ways to do it. If I take the derivative of the first derivative, I get the second derivative. F double prime is one way to write the second derivative. Okay. You can also write it like this. When you take the derivative of the first derivative, okay, this just means the second derivative. Make sure you put the squareds in the right places. Okay, on the top one it goes in between the d and the y. It goes on the d, and on the second one it goes on the x. Okay, both of those mean second derivative when you're finding the second derivative. All right. The last thing that we have to do. Again, this is a common thing too. So you have this, okay? One of these graphs is position. One of these graphs is velocity, and one of them is acceleration. And so what you have to do is try to figure out, you got to pick one to start with and go, all right, let's take the derivative of it and see if it lines up with any of the others. And so let's start with the very first one for A. Okay, there's a couple things about A that we know. This is, if we wanted, we're going to test to see if it's the position. If this is the position, that means there's going to be a 0 and a 0. Okay, which means if this is position, then the velocity graph would have to have 2 zeros. Well, what do we notice about these other 2 graphs? Well, independently. None of them have zeros. There's no 0 here. There's no 0 here. So we know right away this can't be position. Cannot be position because the derivative at this point here is 0 and the derivative at this point here is 0, and neither one of these have zeros. Okay, so let's move on to the next one. Does B have any horizontal tangents? How many? Okay, so it needs to be 0 how many times? Once. What graph has zeros one time? A, okay? So it's possible that this is position and this is velocity. But it's also possible that this is velocity and this is acceleration, okay? Because the derivative of this, so we know that when you take the derivative of B, we're going to get A. We're just not sure which position B is in yet, okay? Now when I look at C, it's almost a horizontal tangent all the way. It's almost zero all the way as we move to the right. But it's positive, okay? So if I was looking at A, it's getting close to zero, but this is negative. If I look at B, as I go to the right, it's still positive because these values above the x-axis are positive, but it's getting very close to zero, okay? And if we go the other way, okay, it starts off really small and it increases, but then levels off. So, if this is position, then this could be its derivative because it never goes to zero, but it gets really close. Okay, it gets really close. The derivative of this gets close to zero, but it goes up right here. And then we already know that A is the derivative of B, so my final answer is going to be C is position, B is velocity, and A is acceleration. Okay? And so when you work through problems like this, now it does say identify and explain your choices. I was doing that verbally for your benefit. Okay, so let's go through it again. So the position starts off as a very small number. So the derivative of this is almost zero, but it's increasing a little bit. So if the derivative is zero and the slope is going up a little bit, right? It's going up, it's going up, it's going up, and then right in about here, it reaches its maximum value. So that's why we see this graph going up, 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 and then right about here, it kind of hits its max. And then the slope starts going down again. It's getting flatter and flatter and flatter, close to zero. And then we already talked about this being a horizontal tangent and that being 1, 0. Okay, so that's kind of the way you want to interpret that. All right. So again, this 2.8, you have homework for it for Friday, but this is the part of our next unit 3. So our test next Wednesday, a week from today, this will not be on it. Okay? But then after that test, we'll have some review and then we'll quiz and kind of go from there. Okay?